Over the years, Yamaha motor products have kept pace with the high-performance demands of today's marketplace. And with products like these, you can expect high technology designed into the systems that deliver that high performance. Ask any technician which motor systems are the most difficult to understand and diagnose, and chances are the answer will be electrical systems. Yamaha electrical systems have become very sophisticated, with circuitry performing a variety of functions, ranging from digital ignition systems that compute variable advanced curves to electronically controlled computer-monitored overheat and over-rev warning systems. While these systems are sophisticated, they all still operate upon the basic principles of electricity, and any technician with a sound grasp of those principles can effectively diagnose, tune, and repair them. The notion that a solid-state transistor-controlled ignition system with its magic black box is any more difficult to troubleshoot simply isn't true, especially when today's electrical systems contain fewer serviceable components than ever. With a basic understanding of electricity itself, electrical components, and how they function in common charging and ignition systems, service technicians can become highly skilled in diagnosing Yamaha electrical systems, and in the process, provide an indispensable service to their dealership. During the first part of this 4-part program, you'll see some basic electrical theory, including Ohm's law and the power formula. You'll learn how electricity is generated into AC and DC current. In Part 2, you'll be introduced to simple electrical components, their symbols and functions. You'll see how those components function in both series and parallel circuits, and you'll learn about the series parallel circuit common to almost all Yamaha products. You'll also learn how to diagnose circuits using voltage, current, and resistance tests, and you'll see how to use and calibrate a multimeter to perform these tests. In Part 3, you'll see how Yamaha charging systems function to generate electricity and how to diagnose single and three-phase charging systems effectively. In Part 4, you'll learn how CDI, or capacitor discharge ignition systems, function, and how TCI, or transistor-controlled ignition systems, function, and how to diagnose each type of ignition system. Finally, you'll learn how ignition controlling components function in ignition circuits, and how to diagnose them as well. Technicians watching this program should have basic arithmetic skills, knowledge of simple laws of physics like pressure and flow, a fundamental knowledge of magnetism, and what materials conduct electricity. It may be a good idea for novices to have a basic electrical text on hand for reference. Now, let's learn what electricity is. Simply stated, electricity is the flow of electrons through a conductor. Voltage, current, and resistance are terms used to describe certain characteristics of this flow. Voltage is the term used to describe the force or pressure available to push electrons through an electrical circuit. Voltage is sometimes referred to as E or EMF for electromotive force. But for simplicity, we'll identify voltage with a V. Current is the term used to describe the rate of flow and is sometimes referred to by an I for intensity. Current is measured in amperes, however, and for simplicity, we'll identify current with the value A. Resistance is the term used to describe the resistance to electrical flow, just as the name implies. Resistance is measured in ohms and sometimes identified by the Greek symbol omega. The relationship between voltage, current, and resistance in the flow of electricity can be demonstrated in an analogy using the flow of water. Imagine that this water storage tank is a battery and the water contained in it represents voltage. If the water level is lowered, the available water pressure or voltage will drop. If the level is raised, the pressure increases. If we open the valve, water will flow through the pipe, which acts as a conductor, to ground level. We might measure this flow of water in, say, liters per minute. In an electrical circuit, this flow would represent current, measured in amperes. The only resistance to this current flow is the size of the pipe or conductor. In our water circuit, resistance is minimal, consisting only of the pipes, which might represent the wires in an electrical circuit. But adding a water turbine to this system will effectively increase resistance and the flow of water will decrease. In an electrical system, this turbine would represent an electrical component such as a starter motor. The relationship between voltage, current, and resistance in an electrical circuit is predictable and governed by a basic law of physics called Ohm's law. Ohm's law states that current flow, voltage, and resistance are related in the flow of electricity. And given any two of these values, we can calculate the third by using this pyramid formula. For example, amperage, or the current flowing through a circuit, is equal to voltage in volts divided by resistance in ohms. Likewise, voltage is equal to current in amps multiplied by resistance in ohms. And resistance in ohms is equal to voltage divided by the current in amps. Now, let's see how Ohm's law can be demonstrated in our water tower analogy. Let's assume the system has 12 volts of pressure and the resistance through the circuit is 20 ohms. To determine the rate, or amperage, of current flow through this circuit, we'd simply divide the voltage, 12 volts, by the resistance, 20 ohms. 12 volts divided by 20 ohms equals 0.6 amperes. The current rate in this system is 0.6 amps. Now, if voltage were increased to 20 volts, how would this affect the current? Voltage is now 20 volts, but resistance remains at 20 ohms. So 20 volts divided by 20 ohms now gives us a current flow of 1 amp. So when voltage is increased and the resistance in the circuit remains constant, current increases. Now let's keep our voltage level at 12 volts, but decrease circuit resistance to 2 ohms. Current flow will now be equal to voltage 12 volts divided by resistance 2 ohms to equal 6 amps. So when voltage is constant and resistance is decreased, current flow increases. Now let's assume that we know both current and resistance values, but not the voltage. Current has been measured at 10 amps, and the circuit resistance is 1.4 ohms. To calculate the voltage, simply multiply the current rate in amps times the resistance in ohms, or in this case 10 amps times 1.4 ohms equals 14 volts. Likewise, if the voltage is known to be 13.8 volts and current is known to be 1.2 amps, resistance would simply be equal to voltage divided by current, or 13.8 volts divided by 1.2 amps equals 11.5 ohms. Another law of physics relating to electricity is the power formula represented in this pyramid. All electrical components, whether they are motorcycle headlight bulbs or a low oil warning buzzer on an outboard motor, consume electrical power at a given rate. This rate of power consumption is expressed in watts, and its symbol is W. Again, our pyramid formula can be used to calculate power consumption, but this time we'll use the values for power in watts, W, current in amperes, A, and pressure and voltage, V. The power formula provides a basic equation for determining power consumption. The power formula states power in watts is equal to circuit current in amperes multiplied by circuit voltage in volts. Going back to our water tower analogy, we can use this power formula to calculate the amount of power in watts consumed by an electrical component represented here by the water turbine. Let's assume the pressure or voltage is 13.8 volts and current is 1.15 amps. To determine the power consumption or wattage of the turbine, simply multiply current, 1.15 amps, by voltage, 13.8 volts, to equal 15.87 watts. Now, to determine current flow, or amps, let's assume that we already know the rate of power consumed by the electrical component is 20 watts. We also know that available pressure, or voltage, is 14.2 volts. Again, using the power formula pyramid, power in watts divided by voltage in volts will give us current flow in amps, or 20 watts divided by 14.2 volts equals 1.4 amps. Let's put this formula to practical use. Suppose you're installing a new headlight on a Yamaha and you need to know which fuse to install to protect it. You've determined that the maximum available voltage in the unit's electrical system is 14.8 volts. The bulb in the headlight has a 50-watt rating, and you want to install a fuse with the proper current value in the circuit. What amp rating should the fuse have? If the power consumed by the lamp equals 50 watts and circuit voltage is 14.8 volts, Wattage divided by voltage, or 50 divided by 14.8, equals 3.37 amps. Therefore, a 4 amp fuse would be suitable to protect this circuit. Let's do a quick review on our two electrical formulas. Using Ohm's law and this pyramid formula, we can determine resistance by dividing voltage by amperage. We can likewise determine current flow in amps by dividing voltage by resistance in ohms. Finally, we can determine voltage by multiplying current in amperes times resistance in ohms. With our power formula, we can determine voltage by dividing wattage by amps. Current in amps can be calculated by dividing power in watts by voltage. Finally, we can determine power consumption in watts by multiplying current in amps times voltage. Now, let's look at generating electricity. Electricity can be generated in a variety of ways, but for purposes of this program, we'll examine how electricity is generated mechanically. Generating electricity mechanically involves moving a conductor through a magnetic field, or in the case of an alternator, moving the magnetic field over a conductor. This diagram represents a simple AC alternator similar to those found on many Yamaha models. The rotor on this alternator contains 4 permanent magnets. These magnets are arranged in such a way that alternating north and south poles face toward the center of the rotor. Magnetic lines of force, or flux lines, flow between these poles. They always flow from the north pole to a south pole and are most concentrated in the area shown here. The alternator's conductor, or coil, is a static component that is really little more than copper wire that has been wound many times around an iron core. The wire itself is insulated from all the other windings and from the iron core. As the rotor turns, the lines of magnetic force pass through the windings of the coil and electromotive force, or voltage, is produced. When this coil is connected to an electrical circuit, voltage will cause electrons to move and current will flow. The current produced here is AC, or alternating current. Because the electrons in this circuit flow in one direction and then reverse and flow in the other, the current generated in this circuit is called alternating current, AC. Let's take a closer look at how and why alternating current is generated. With the rotor positioned as shown here, the concentrated lines of magnetic force directly over the face of magnet 1 are not yet acting on the coil windings. At this point, the lines of force created between magnets 1 and 4 are running parallel to the winding, and voltage is 0. As the rotor continues to turn, the coil is subjected to a greater portion of the concentrated field, and voltage begins to rise. At this point, the coil is subjected to the full force of the field created between magnet number 1, the north magnet, and magnets 2 and 4, both south magnets. Notice that the flux lines are flowing out from the magnet positioned directly adjacent to the coil. At this point, voltage reaches its positive maximum as indicated on the graph. As the rotor continues to turn, the field's effect on the coil is lessened, and voltage begins to fall until finally the lines of magnetic force are again running parallel to the winding and voltage returns to 0. At this point, the number 2 magnet, which is a south pole, is beginning to come into play. Voltage is again being produced, but this time, because the lines of magnetic force are flowing from 2 north poles, magnets 1 and 3, to a south pole, magnet 2, the flow of current is reversed. As the rotor turns still further, the windings are again subjected to the full concentrated strength of the field, and voltage reaches its negative maximum. Further rotation of the rotor reduces the number of flux lines acting on the coil, and voltage begins to drop until finally the effect of the field on the windings is reduced to 0. This alternating cycle, where voltage increases to maximum positive, decreases to 0, increases again to maximum negative, and decreases again to 0, is referred to as an AC cycle. This particular alternator, which has only one coil, is referred to as a single-phase alternator and is seen on simpler motors. Products requiring increased power output use three-phase systems, which incorporate 3 single-phase circuits working simultaneously and will be examined later in this program during the explanation of charging systems. The amount of voltage produced by any alternator or generator is dependent on three factors: the strength of the magnetic field, the speed at which the magnetic field passes through the windings, or in this case how fast the rotor turns, and the number of wire turns contained in the coil. The diameter of the wire used will also affect current flow. As we'll see later, some Yamaha ignition and lighting systems do operate on AC or alternating current, but circuits requiring a battery to operate components without the engine running require direct or DC current. For these applications, it's necessary to convert or rectify the AC current to DC or direct current. Completing an alternator circuit by connecting one end of the coil wire to ground and the other to the unit's electrical system will allow alternating current to flow back and forth in the circuit. When a diode, which we'll learn later is simply a one-way electrical valve, is placed in line in the circuit leading to the electrical system, only the positive pulses in the AC current will pass, and the negative pulses in the cycle remain unused. This circuit would be referred to as a half-wave rectified circuit. Current supplied to the electrical system through this circuit is referred to as pulsating DC. To make use of all the coil's output, both the positive and negative portions of the AC cycle, it would be necessary to install a full-wave rectifier in the circuit. To change alternating current to full-wave rectified DC current, a minimum of 2 diodes is necessary for each stator lead in the circuit. As you can see, both coil leads are now connected to a 4-diode rectifier, and both the positive and negative AC pulses are now being used to produce DC current, which flows consistently in one direction to the battery in order to provide more power to operating system components. In Part 2 of this program, you'll be introduced to simple electrical components, their functions, and symbols. You'll see how these components function in both series and parallel circuits, and you'll learn about the series parallel circuit common to almost all Yamaha products. You'll also learn how to diagnose circuits using voltage, current, and resistance tests, and you'll see how to use and calibrate a multimeter to perform these tests. Now let's look at some typical components found in most Yamaha products, their functions, and their electronic symbols. This is the symbol, for example, for a battery with positive and negative terminals indicated. These symbols both indicate ground. The ground on the left indicates a connection to a common ground wire or circuit, and the ground on the right symbolizes a direct ground to the product's chassis or frame. The symbol on the left in this graphic designates a single lead switch of the type commonly used in Yamaha brake lights, neutral lights, and engine cutoff circuits. The component in the center designates a multiple lead switch and usually shows 2 or more switch positions, as well as which circuits are connected in each switch position. The symbol on the right indicates a fluid level switch that is part of a fluid level monitor, such as a low oil warning light switch. Like the switch on the left, this fluid level switch is also a single lead type with a slightly different symbol to indicate that it is a fluid level switch. Lamps or light bulbs are components found in almost every Yamaha wiring diagram. Symbol number 1 represents the element of a simple light bulb. Symbol 2 is similar, but because it has more turns, it represents a coil or winding. This symbol is used to indicate stator, motor, and ignition coil windings, which you'll learn more about later. Symbol number 3 represents a resistor, also found in almost every Yamaha. Resistors are commonly found in voltage regulators, both mechanical and electronic. The fourth component shown here is a variable resistor, commonly found in fuel gauge circuits. This symbol depicts a capacitor, which is a component which stores an electrical charge. A capacitor acts as an electronic sponge, soaking up a charge to release it later. These symbols represent 2 components designed to protect electrical circuits. The component on the left is a common, non-reusable fuse designed to burn out before a more important circuit does. The symbol on the right represents a circuit breaker, which, as the name implies, breaks a circuit temporarily to protect it. Circuit breakers, unlike fuses, can be reset. This symbol represents another component common to Yamahas, an electromagnetic switch, often called a relay or solenoid switch. Relays are designed to control current flow in a given circuit from a remote switch location. This starter circuit is an example of an application of a relay switch. Starter motors usually require large amounts of current. The initial heavy draw of current a starter motor needs may exceed 90 amps in some cases. With heavy current flow, a heavy gauge wire is required to handle this current flow, and a switch capable of handling that sort of amperage would have to be quite large. So, in order to avoid large amounts of heavy gauge wire and huge switches, a remote control switch is used to activate the main starter circuit. When the remote starter switch is pushed, current flows through a series of windings contained inside the relay switch. This current flow creates an electromagnetic field which acts as a magnet on the main portion of the relay switch, pulling it closed. This completes a direct circuit between the battery and the starter motor, and the motor will turn. When the starter button is released, current flow to the coil in the relay stops. The magnetic field is eliminated, and the main portion of the relay opens again, cutting off the current flow to the starter motor. You'll learn more about relays later when we discuss ignition controlling components. This symbol represents a diode, which acts as a one-way electrical valve that allows current to flow freely in one direction only. Resistance to the current flow in the reverse direction is extremely high. Diodes are used in many Yamaha circuits, but their most common use is in AC to DC voltage rectifiers. By taking this simple diode symbol and adding a line like this, we can change the symbol to a thyristor. A thyristor also allows current to flow in one direction only, but has an additional function of acting as a control gate. The thyristor will resist all current flow until a small voltage is applied to the component, which then allows current to flow in the prescribed direction. Another variation on a diode is the Zener diode. A Zener diode also allows current to flow in only one direction, but it is also designed to resist the backward flow of current up to a certain voltage level, where it then becomes conductive in both directions. When voltage levels in the circuit return to normal, the Zener diode resumes its normal single-direction state. Zener diodes are commonly used in AC lighting circuits to protect lights from current overloads. This circuit represents a simple series circuit. A series circuit is defined as a circuit with one or more load devices, but only one path through which current may flow. In this series circuit, we have a battery as a power source and 4 light bulbs wired in series. Current is forced to flow from the source through each bulb in series and finally to ground. If one bulb burns out, the current flow is broken and we'd have an incomplete or open circuit. Each bulb in the series circuit is dependent on the others being in operating condition. This is a parallel circuit. A parallel circuit consists of a power source, in this case a battery, and a number of components, in this case lights. Each component in a parallel circuit draws its power from a common wire, but current can flow to each and to ground without first flowing through another component. Simply stated, a parallel circuit is one with 2 or more components, each with its own individual path for current flow. If, for example, one of these lights were to burn out, current would continue to flow to the others. A common type of circuit found in many Yamaha electrical systems is the series parallel circuit, a simple combination of both series and parallel circuits. This signal light circuit is a good example. The main fuse, main switch, circuit fuse, flasher unit, and signal switch are wired in series in this circuit. Current must flow along one path through each unit to reach the next. On the other side of the signal light switch, there are 2 individual parallel circuits, one consisting of the left indicator and signal lights, and the other containing the right indicator and signal lights. In these parallel circuits, each light operates independently of the others, and if one light fails, the others will remain lit. As we test these circuits, there are 3 main problems that can occur. A circuit may be shorted, it may be open, or there may be excessive resistance in the circuit. A short circuit, by definition, is one where there is too little resistance in relation to the available voltage. Again, using our signal light circuit, let's assume that the wire leading to the left front signal light has broken and is contacting a portion of the frame. We'll also assume that this contact is sufficient to allow current to flow completely unrestricted. Because electricity will always seek out a path offering the least resistance, when the left signal lights are turned on, current will flow directly to ground through this contact point or short. Since there is virtually no resistance to current flow, amperage will increase until either the wire conductor is destroyed as a result of the excess flow of current, or the fuse element melts. The term short circuit really says it all. The normal path of current flow through the circuit is shortened, and resistance to this flow is drastically reduced. An open circuit, by definition, is one that is incomplete in that the normal path of current flow is interrupted. As an example, if the wire between the flasher relay and the signal light switch were cut, but not touching a ground element, this circuit would be incomplete or open. The gap between the two wire ends would consist of nothing more than air, and since air is an extremely poor conductor of electricity, resistance measured between these two components would be total or infinite. Occasionally, a circuit may not be open or completely shorted, but simply have an excessive resistance at some point. Remember, whenever resistance in a circuit is increased, current flow will decrease. If, for example, resistance across this ground connection was excessive, current flow through this light bulb would be reduced. The light would remain lit, but it would not be as bright as the others in the circuit. Circuit problems such as opens, shorts, and excessive resistance can easily be diagnosed with proper circuit testing. If, for example, a dimming light caused you to suspect the available line voltage in the lighting circuit, a simple voltage test will confirm line voltage. Voltage tests and other circuit tests are generally performed with a multimeter like this one. A multimeter is actually a voltmeter, an amp meter, and an ohm meter all in one. Analog or needle multimeters like this one are in common use and must be calibrated regularly. Digital multimeters offer the advantages of higher degrees of accuracy and a broader scale selection. Both types of meters require that their batteries be in good condition for accurate testing. Another general point to remember when using multimeters is to always start metering at the highest scale available, especially when you're not certain about the amount of voltage or amperage in the circuit to be tested. When testing a circuit for voltage, the multimeter is always connected in parallel to the circuit. In this circuit using direct current of less than 20 volts, the meter should be set to the DC 20-volt scale. The meter should then be connected in parallel to the circuit by connecting the positive red lead from the positive meter terminal to the circuit wire, and the black negative lead from the negative meter terminal to a common ground. The resulting meter reading will indicate line voltage in the circuit. To perform a current or amp test, always select the highest DC amp scale, in this case the DC 10 amp scale. Current tests are always performed with a multimeter connected in series to the circuit being tested. When the meter is connected in series, the current flowing through the circuit must also pass through the meter. During a current test, the appropriate connector or component is disconnected and the meter's black or negative lead is attached to the load side of the circuit. The positive red lead is then connected to the positive DC amp terminal on the meter, and then in series to the power source side of the circuit. Once the circuit is switched on, the meter will measure the current flow through the circuit. If the indicated amperage is relatively low, in this case just under 4 amps, you can switch the meter to a lower scale for a more accurate reading, here 3.6 amps. When testing a circuit for resistance, the multimeter is used as an ohm meter to measure resistance through a circuit or through an individual component. Resistance tests must be done on circuits or components that are not active. Using the multimeter to measure resistance on a live circuit or component will damage it. Remember it this way: resist the temptation to connect the multimeter to a live circuit for a resistance test. Resistance tests also require a calibrated meter before testing, and each time the scale is changed. To calibrate the ohm meter, connect the leads to their appropriate multimeter terminals as shown here. Switch the meter to the ohms times 100 scale and connect the 2-meter leads. The ohms adjust or ohms calibration knob is then used to bring the needle to zero. Testing a circuit or component for resistance is then a simple matter of connecting 1 meter lead to each end of the component or circuit to be tested. If resistance is too low to be read accurately on the high scale, switch to a lower scale, recalibrate the meter, and retest. Occasionally, you may need to check the resistance of a component while it is under load of a live circuit. Because electrical components like switches, coils, and connectors often heat up and develop much higher resistances under load, they can only be tested accurately during operation. To test a live circuit or a component for resistance without destroying your ohm meter, you can use an indirect method called the voltage drop test. The term voltage drop is used to describe the natural drop in voltage when current is pushed through an operating electrical component. Remember, due to Ohm's law, when resistance is decreased in a circuit and current remains the same, voltage must drop. To further explain this relationship between resistance and voltage, let's consider a circuit with 12 volts line voltage and 2 components in series, each having a resistance of 10 ohms. The total resistance in the circuit would be 20 ohms. And since the 2 components have equal resistance, half the circuit's voltage, in this case 6 volts, would be used up in pushing current through the first resistor, and the remaining 6 volts would be used for the second resistor. If the resistance of the components here was changed to 5 ohms and 15 ohms respectively, then the voltage used by each component would be 3 and 9 volts respectively. From Ohm's law, you can see that the voltage used to push current through an electrical component is proportional to the resistance of the component. Because the voltage will drop in direct proportion to the resistance of the component tested, using the voltmeter in this manner allows an indirect measurement of resistance across any component while the circuit is working. Let's see an example of an indirect resistance test using the voltage drop method. With the meter set to a high DC voltage scale, the meter leads are connected across the terminals of this starter relay, in this case. When the circuit is activated, the relay switch will exhibit normal resistance when the voltage drops to approximately 0.2 of a volt. This voltage drop reading may vary, of course, depending on the resistance or load rating of the component being tested. This program was produced for Yamaha dealers and their qualified technicians. It is not intended to be provided to retail customers. This program is intended only as an audiovisual overview. It does not replace the skill and knowledge of a qualified technician. This program also does not replace the comprehensive procedures and safety information provided in Yamaha service publications. Be sure to read the appropriate publications for the product and all labels on the product before beginning any service work. In Part 3 of this program, you'll be introduced to 2 types of charging systems found on Yamahas. The permanent magnet type, which uses a heavy flywheel containing several permanent magnets fixed in pairs. Both single-phase and 3-phase permanent magnet charging systems will be explained. You'll also learn about the electromagnet type charging system, which uses a field coil to produce a variable magnetic field. Electromagnetic field coil charging systems are all 3-phase and are found on larger motor products having more accessories. Single-phase permanent magnet charging systems are usually simple circuits consisting of a permanent magnet rotor, a charging coil, a rectifier, and the battery. A single-phase permanent magnet charging system like this one is mostly used on small to medium single-cylinder motors common to Yamaha ATVs, snowmobiles, outboard motors, and golf cars. The advantages of single-phase permanent magnet charging systems are their simplicity and low cost. To understand how a permanent magnet charging system operates, let's review briefly how electricity is generated. Remember, alternating current is generated in the windings of a charging coil and is diverted to AC lighting circuits and other AC components. Some Yamaha equipped with AC lighting use a single-phase, half-wave, permanent magnet charging system. On these models, both the lighting system and the battery charging system rely on power generated by a single charge coil. Therefore, a problem that occurs in either system could affect the operation of the other. AC is routed through a half-wave rectifier which supplies direct current to the battery and DC circuits. As the speed of the rotor increases, both voltage and current also increase. But in a single-phase half-wave permanent magnet charging system, the design of the coil itself limits the amount of energy produced. At idle, for example, the voltage generated may be somewhat below the voltage that the system requires during normal operation. As the RPM rises to 2,000 to 3,000 RPM, voltage will rise high enough to meet system demands. And at higher RPMs, voltage and current may even exceed what the system needs. At some RPM, the single-phase half-wave coil will become less efficient and simply cannot produce any additional power the system may require. If extra electrical accessories or equipment are connected, a continuous battery discharge may result in a non-regulated system like this. Likewise, removing a component or some electrical load may result in overcharging the battery. A Zener diode is often placed in line in the AC lighting circuit like this one to prevent sudden voltage overloads or spikes to lighting components. Single-phase, half-wave permanent magnet systems are susceptible to resistance problems in the charging circuit. For example, resistance through the connection between the coil and rectifier might be excessive. This increased resistance will result in a loss of voltage across the connection, and the excessive resistance here will decrease the amount of power reaching the rectifier. The result will be an insufficient supply of energy to keep pace with the demands of the electrical system, and the battery will likely discharge over a short period of time. In addition, the higher the normal resistance in this non-regulated system will cause heat to build up in the stator coil, which could result in permanent damage to the coil windings. If the unit is equipped with an AC lighting circuit, current, unable to pass through the rectifier, may back up into the lighting circuits and quickly destroy light bulbs. Diagnosing problems in a single-phase half-wave permanent magnet charging system is simply a matter of checking the operation of each component in the system. Always check battery condition first on a system like this. If the battery is in good condition and fully charged, perform an amp test on the charging system under operation. If your amp test determines that the charging system's output is below the specification for the circuit, proceed to diagnose the charging coil itself with a resistance test. If the coil proves to be in good condition, the rectifier must be suspected, as it is the only component remaining in the charging system. Check the positive lead from the battery to the rectifier for continuity. Then check the charge coil lead to the negative rectifier lead for continuity. If the lead tests good, the rectifier must be suspected, as it is the only component remaining in the charging system. Rectifiers are usually replaced as a unit, but you can test this component for resistance through its diodes. This system uses a half-wave rectifier containing one diode, which must be tested for continuity in both directions, verifying that current is allowed to flow in one direction and not the other. Be careful when testing rectifiers. They can easily be destroyed if subjected to overloading. Short-circuiting the rectifier leads or reversing the polarity of battery leads can also damage a rectifier. Remember, resist the temptation to perform a resistance test on a live circuit and disconnect the rectifier first from the unit's charging system. Use the ohm meter on the ×1 scale and connect one lead of the multimeter to the input lead from the coil to the rectifier. When the other lead is connected to the rectifier's output side, the ohm meter should read either a measurable resistance or infinite resistance, depending on the polarity of your meter. If the diode shows a measurable resistance in one direction, it should show infinite resistance when the meter leads are reversed. Test the diode in the rectifier in the same way, reversing polarity to check the diode in both directions. If the diode in the rectifier proves bad, you'll have to replace the rectifier as a unit since its diode is not serviceable. To overcome the limitations built into this single-phase, half-wave permanent magnet charging system, many Yamahas feature single-phase, full-wave permanent magnet charging systems. In a full-wave system, a full-wave rectifier is used to capture the full AC cycle, or wave, from the charge coil, which doubles the energy generated in a half-wave system. To regulate this increased output, a voltage regulator is used to continuously control current flow to the entire electrical system. The voltage regulator is usually combined with the full-wave rectifier that supplies DC current to the system. The regulator, by routing excess current to ground, maintains optimum circuit voltage and current at any engine speed. Voltage-regulated systems can be identified by charge coils that have both leads connected to the rectifier to allow the charging system to respond to increased power demands under load. Diagnosing problems in a full-wave regulated charging system involves the same steps as that of a half-wave non-regulated system. Check battery condition, then perform a current test on the system during operation. Test the charge coil for proper resistance and check it for a short to ground. Test the lead wire from the rectifier to the battery for 12 volts. Test the rectifier's ground lead for continuity. If these components and leads test good, you can presume the regulator rectifier is bad by process of elimination and should be replaced. Single-phase charging systems provide sufficient electrical power for smaller motor products, but larger products often require more power to meet the demands of sophisticated electrical systems or to power any number of accessories. By using more coils in a charging system, more power can be generated at all RPMs. These multiple coil charging systems are called three-phase charging systems. In a three-phase system like this, a stator assembly containing 3 charging circuits is used. Here, 18 coils form 3 sets of 6 coils each. Each coil set is effectively one single-phase circuit, 3-phase then being 3 single-phase circuits working simultaneously. Although the symbol in the lower left corner is normally used to represent a 3-phase system, we've chosen to depict a 3-phase system with this diagram because it more accurately represents an actual multi-coil 3-phase stator. Each set of connected coils is depicted in a different color to identify each stator circuit. Because a 3-phase full-wave charging system like this produces AC cycles in multiples of 3, the rectifier used contains 6 diodes. Each AC cycle is then full-wave rectified to direct current, DC. Again, the voltage regulator rectifier component monitors system voltage and routes any excess current flow to ground. Aside from the fact that this 3-phase system uses 3 charging coils and a 6-element rectifier, diagnosing problems on a 3-phase circuit is no more difficult in principle than on a single-phase system. Test the battery first for proper charge, then test the system current output. If current flow is abnormal, proceed to check each charging circuit for continuity by disconnecting it from the system. To check each stator circuit, you'll have to perform several resistance tests. 3 to determine resistance through the stator circuits, and 1 to determine if any of the windings are shorted. Connect 1 meter lead to the number 1 stator lead and the other to the number 2 stator lead. The stator coils shown here in yellow and orange are connected in series, and this test actually checks the combined resistance of the two. Switch the leads to check the second circuit. This test checks the combined resistance of the yellow and blue coils. Finally, the third set is checked in the same manner. To complete your stator test, attach 1 ohm meter lead to ground and check any one circuit for a short. Since none of these circuits is connected to ground, a resistance test should indicate infinite resistance. If continuity, that is, no resistance is indicated, one of the circuits is shorted. If the short is found to be located in the harness leading to the windings, the short can be repaired and the stator assembly may be salvaged. But if any of these stator coils has a short to ground or proves faulty, the entire stator assembly will have to be replaced as a unit. If the coils prove good, the voltage regulator rectifier must be suspected by process of elimination. Test the voltage at the lead that supplies the regulator rectifier for system voltage 12 volts. Then, check the regulator rectifier's ground lead for continuity. If the leads are good, replace the regulator rectifier. Now let's examine electromagnetic charging systems. Earlier, you learned that single-phase permanent magnet charging systems generate electricity using a coil of wire, a magnetic field, and motion between the two. The amount of energy produced was dependent on the size of the coil, the strength of the magnetic field, and the speed at which the field passes through the windings of a coil. If more power is needed, however, this single-coil, single-phase system is limited in power output since the number of windings contained in the coil can't be varied. But by using an electromagnet rather than a permanent magnet and varying the amount of current passing through the windings of an electromagnetic coil, the strength of the magnetic field can be increased and the amount of energy the alternator produces can be varied as needed by the electrical system. Yamaha electromagnetic charging systems generally feature a crankshaft-mounted rotor that revolves within a stator coil to produce the necessary generating motion between the magnetic field and the conductor. The strength of the field is controlled by the amount of current being supplied to the winding through the voltage regulator. Current is delivered to the rotor itself through a pair of carbon brushes running on two slip rings. Current flows into the rotor through one brush and slip ring and out through the other to the voltage regulator, then to the ground. When the unit's main or ignition switch is turned on, current flows directly from the battery through the field coil windings through the voltage regulator to ground. Since full battery voltage is applied to the coil, the magnetic field produced is very strong. When the motor is started, the rotation of the rotor between the field coil and the stator induces voltage in the stator windings, and current is generated in all three stator circuits. This AC current then passes through a 6-element rectifier and is converted to DC current. At this point, depending on the battery's state of charge, the regulator may slightly increase or decrease the amount of current being supplied to the field, thereby slightly increasing or decreasing the field's strength and alternator output. The amount of current generated in this electromagnetic charging system will increase with engine speed, and as this occurs, the voltage regulator senses the increase and begins to reduce the strength of the field by reducing the amount of current being fed to the field coil. As a result, field strength is reduced and stator output is regulated to the required level. At moderate to high speeds, the regulator will further reduce the strength of the field and again, output will meet required levels. The voltage regulator will also sense additional circuit loads and adjust output accordingly. Three-phase electromagnetic charging systems are diagnosed in a manner similar to the three-phase permanent magnet systems you learned about earlier. The battery's charge should be checked. Next, a current test should be performed on the system under operation. A system with abnormally high current almost always points to a faulty voltage regulator. If the system current is below normal, test the field coil. A quick check of general field coil condition is to hold a feeler gauge near the alternator housing and turn the main switch on. If the magnetic field produced by the coil is strong enough to attract the gauge, chances are both the brushes and the coil are in good condition. If the magnetic field is weak, a resistance test on the field coil lead should be performed. Disconnect the field coil from the system and check the coil for continuity and for shorts, as you learned earlier. If the field coil tests good, proceed to test the stator. Some Yamahas use a pulse from one stator winding to produce a tachometer signal. Because it may affect resistance levels, the tach lead should be disconnected before checking the stator for resistance. Also, check the stator for a short to ground. Test the positive lead from the battery to the regulator rectifier for system voltage, 12 volts, and also test the negative ground lead from the regulator for continuity. If all the leads and components in the system test good, the only component remaining to affect the charging system is the voltage regulator rectifier, and as before, this unit cannot be serviced. If all the other components and leads test good, replace the regulator rectifier. In Part 4 of this program, you'll be introduced to both CDI, or Capacitor Discharge Ignition Systems, and TCI, or Transistor Controlled Ignition Systems. And you'll learn how they function and how to diagnose them. You'll also learn about various ignition controlling components, how they function, and how to diagnose circuits containing them. Ignition systems in general can be divided into two groups: self-powered ignition systems and battery-powered ignition systems. These can be further divided into mechanical and solid-state systems, but for purposes of this program, we'll only concern ourselves with solid-state ignition systems. Let's start with the self-powered variety. The CDI, or Capacitor Discharge Ignition System, is self-powered, meaning it does not require an external power source like a battery to operate. CDI systems are simple and economical for use on smaller motor products that don't place great demands on ignition controls. The main components of a CDI ignition system are the pulsar coil, the charge coil, the capacitor, and thyristor, which are contained together in a single ignition unit, and the primary and secondary windings in the ignition coil, and the spark plug or plugs. In a CDI system, AC voltage is produced when the rotor magnets pass over the charge coil. Current flows through a diode in the CDI ignition unit and is allowed to build up in the capacitor, which acts as an electronic sponge, soaking up a charge. The amount of energy stored in the capacitor increases each time a magnet swings past the windings of the charge coil. As the crankshaft continues to turn, the rotor swings past the pulsar coil, producing an AC signal. This AC signal passes through a diode and supplies DC voltage to the thyristor. The signal makes the thyristor conductive, and all the energy built up in the capacitor is suddenly released to the primary side of the ignition coil. The resulting field expansion occurs with tremendous speed, and the high voltage induced in the secondary winding produces a very strong spark. On some CDI ignition systems, a single coil is used to fire two plugs simultaneously as a pair. This component is called a dual lead coil, or a Siamese coil. Diagnosing problems in a CDI circuit requires component testing using Yamaha's Y1 tester. The Y1 tester allows tests of components under load that cannot be easily accomplished with a standard multimeter. The scale on the Y1 tester indicates only relative electronic values and does not indicate volts, amps, ohms, or watts. Consult Yamaha's service literature for your model's Y1 test specs. After the Y1 tester has been set to the appropriate range and spec, test the system's pulsar coil first. Attach the Y1 tester leads to the pulsar coil lead and then turn on the ignition and turn over the motor. If the indicator on the Y1 tester lights up, the pulsar coil is good. If the indicator doesn't light, though, don't presume the component is bad. First, disconnect the component, in this case the pulsar coil, from the system and test it again on the Y1 tester outside the system. If the coil fails outside the system, it's bad and should be replaced. If the coil tests good on the Y1 tester outside the system, don't presume the component is good. It could still have a short to ground. Use the multimeter as an ohm meter to test for proper resistance by attaching one meter lead to either end of the coil and the other lead to ground. Some Yamaha pulsar coils have both leads connected to the CDI box. Test these pulsars for proper resistance in the coil and also for a short to ground by connecting one lead on the ohm meter to one of the coil leads and the other to the ground. If the coil has normal resistance, proceed to the next component in the system, the charge coil. Use the Y1 tester at the charge coil and test the charge coil dynamically and disconnect it from the system. Use the ohm meter to check the charge coil for a specified resistance. Again, charge coils on some Yamaha products have both leads attached to the CDI unit. On these coils, use the ohm meter to test resistance through the coil and then check the coil for a short to ground as with the pulsar coil. If the charge coil proves faulty, replace it. If the charge coil tests good, proceed to test the output of the CDI box itself. CDI systems can be damaged if their output leads aren't loaded, so be sure the CDI pack is always connected to the system, a load coil, or the Y1 tester before cranking the motor. If the CDI pack lights the Y1 indicator, the unit is good. If the CDI pack fails the system test, however, don't presume it's bad. Other faulty components in the system might be affecting it. And since the CDI pack can't be tested outside the system, it can only be isolated as the problem component by eliminating all the other possible problems in the circuit. Test the ignition coil last in a CDI system. Ignition coils must be tested dynamically on a coil checker. If the ignition coil tests bad, replace it. Dual lead coils should be tested for resistance by connecting one ohmmeter lead to each high voltage output lead. CDI ignition systems are especially prone to problems resulting from high resistance somewhere in the circuit. Test all leads and connectors for possible opens or shorts to ground. If the dynamic coil test proves the ignition coil is good, however, and the system still exhibits a problem and all the other leads and components have tested good, the CDI unit must be faulty by process of elimination. Now let's examine the components and functions of battery-powered ignition systems. Again, we'll focus our attention and discussion on solid-state systems represented by the TCI, or transistor-controlled ignition system, which have become common if not standard on most large Yamaha motorcycles. TCI systems consist of several components, including a reluctor, which is a projection on the rotor which sends a timing signal to the pulsar coil. The TCI unit itself acts as a timing and advanced control unit to signal the secondary circuit to provide ignition spark. Past the TCI unit, the ignition system is similar to CDI systems, consisting of a coil and spark plugs. TCI functions begin when the ignition switch is activated, which supplies current from the battery to the TCI unit and also to the primary side of the ignition coil and through the TCI unit to ground. As with other ignition systems, a magnetic field around the primary winding is allowed to expand and collapse, inducing high voltage in the secondary circuit to produce a spark. As the crankshaft turns, the rotor swings past the pulsar coil and generates a signal pulse which is transmitted to the TCI unit. There, the signal pulse triggers a transistor switch which cuts the ground to the primary circuit. Since the primary circuit is no longer complete, current flow stops and the field around the primary winding collapses, creating the ignition spark. As the reluctor swings away from the pulsar coil, the pulsar signal is eliminated. This causes the TCI unit to again allow primary current to flow to ground. The primary field builds and the cycle begins again. By taking this simple TCI system and adding 3 more pulsar coils, an additional reluctor and 3 more ignition coils, we can represent the ignition system found on some 4-cylinder Yamaha products. Because each cylinder has its own ignition system in effect, the TCI system is very reliable. Many Yamaha motors utilize dual lead coils with the TCI ignition system. Here, 2 pulsar coils alternately control current flow through a pair of dual lead ignition coils. When the ignition is turned on, current is supplied to the TCI control unit as well as the primary circuit for one of the ignition coils. As the reluctor passes over the number 1 and number 4 pulsar, current to the number 1 and number 4 coil is switched off, creating the ignition spark. At the same time, current to the primary side of the number 2 and 3 coil is switched on. As the reluctor swings past the second pulse coil, the signal produced causes the control unit to switch the current flow to the number 2 and 3 coil off, again producing an ignition spark at the same time the reluctor switches current back on to the number 1 and 4 coil. With this system, if one pulse coil fails, the entire system will be rendered inoperative. The operating pulsar will switch the current on, but without the signal from the second pulsar, current is not switched off. There's no field collapse and therefore no ignition spark. Diagnosing problems in a TCI ignition system is no more complicated than the systems you've already seen. Test the battery for proper voltage and charge. If the battery is serviceable, test the plugs for good spark, and the appropriate leads and connectors for excessive resistance. Resistance tests should then be performed on each individual pulsar coil and the primary and secondary windings of each ignition coil. Then perform a voltage test for 12 volts at the lead supplying the TCI unit with system voltage. Also, check voltage at the input lead to each ignition coil for 12 volts. Again, if the leads and all other components and connectors test good, the TCI unit itself must be suspect. Like the CDI system unit, the TCI unit can't be tested with common test equipment. If you've systematically eliminated all the other components and the system is still faulty, you can assume the TCI unit itself is faulty and should be replaced. We've seen how CDI and TCI ignition systems operate and covered some basic diagnosis of ignition-producing components. Now, let's examine some ignition controlling components that are common to both systems and to many Yamahas. Ignition controlling components may be as simple as an engine shutoff switch, or they may be as complex as a series of safety interlock relays that control the conditions under which ignition is permitted on this motorcycle ignition circuit. If ignition controlling components like the neutral switch or the side stand switch in this circuit are faulty, they can prevent the ignition system from operating properly. For example, in this diagram, the side stand circuit consists of the side stand switch and the side stand relay. As shown here, both the side stand and neutral switches are open, indicating the side stand is down and the transmission is in gear. Under these conditions, the motorcycle's ignition and starter circuits are designed to be inoperative. When the ignition is turned on, current will flow directly through the primary ignition coil winding, the TCI igniter unit, and the side stand relay to a ground that renders the ignition unit inoperative. This ground prevents normal igniter unit operation, which prevents the primary field in the coil from collapsing and therefore preventing ignition spark, and the unit will not start. However, if the side stand is retracted properly, the side stand switch closes, completing the circuit through the side stand relay. The relay becomes activated and opens, eliminating the abnormal ground at the TCI igniter unit. If ignition controlling components like the neutral switch or the side stand switch in this circuit are faulty, they can prevent the ignition system from operating properly. To diagnose and locate an ignition system problem that you suspect may be caused by an ignition controlling component, the standard procedure is simply to disconnect or bypass each component in turn from the interlock circuit and then test the circuit's operation. If the ignition system still exhibits the same problem, test the next component in line. In this ignition system, the side stand switch would be disconnected and the system tested without it. Key switches, side stand switches, and other easily accessible ignition controlling components are usually diagnosed first. If these components test good, side stand relays, neutral switches, and other less accessible ignition controlling devices should be tested after eliminating the simple solutions. If the unit runs better without the ignition controlling component, you have isolated the cause of the malfunction and the component should be replaced. During the course of this program, you've been introduced to basic electrical theory, simple electrical components found on most Yamahas, and some circuits common to many Yamahas. You've learned about non-regulated single-phase charging systems and regulated three-phase systems. And you've learned about CDI and TCI ignition systems, ignition controlling components, and how to diagnose them. With this knowledge and some experience to sharpen your skills, you can soon become proficient in diagnosing and repairing Yamaha electrical systems. You'll provide a valuable service to your dealership, and nobody will appreciate your technical skills on a Yamaha more than